Nanotechnology is a part of some of the tremendous amount of technological research that is ongoing aboard the International Space Station, which serves as not only an orbital laboratory, but as a test bed for technological research that will serve us in exploration of the planets and an asteroid and deep space in the years ahead. One of the unique technology demonstration capabilities of the International Space Station also extends to the outside of the orbiting complex in the form of a robot. The Satellite Servicing Capabilities Office at NASA's Goddard Space Flight Center in Greenbelt, Maryland, oversees the Robotic Refueling Mission demonstrations on the station. And Jill McGuire, the RRM project manager, is joining us this morning on Space Station Live to talk about it. Jill, good morning, and thanks for joining us today.
Thank you very much for having me. It's a pleasure to be here.
Great to have you with us today, Jill. The Robotic Refueling Mission suite of experiments is not new, but it is somewhat familiar to those of us who are paying attention. Give us a little glimpse about what the Robotic Refueling Mission is and what it does on board.
So the Robotic Refueling Mission is a payload about the size of 1 meter cube. It's on ISS on ELC-4, and it has various spacecraft interfaces on it that we've used to test out robotic manipulation techniques to demonstrate the feasibility of using a robot to refuel, repair, and maintain satellites in space. We've completed numerous demonstrations, including wire cutting, cap removal, blanket manipulation, and finally an end-to-end fuel transfer about a year ago. And we are looking forward to continuing that with RRM-2, and that's what we are to talk about today. Some of our new hardware has just been recently launched on ATV-5. So the photo of RRM that is up on the screen, in that you can see that there are 4 different tools on board that the Dexter robot, the Canadian robot, uses to do these demonstrations. And RRM is designed to be modular so that we can switch out those tools and we can switch out the task boards in order to do additional experiments, which is what we're taking advantage of for RRM-2.
Jill, refueling or fuel transfer is not new to human spaceflight. In fact, as you mentioned, the automated transfer vehicle that brought your new hardware up, as well as the Russian Progress vehicle, contains fuel that is transferred for a variety of purposes. But there are still unknowns to this art in human spaceflight. Why is orbital refueling so complex?
Well, the reason it's complex is because the interface was not designed to be robotic friendly. A fuel valve on a satellite is closed out before launch with a series of caps, and then those caps are wired shut. Because the fuel is so flammable, they want to make sure that the interface is safe during launch and that those caps can't back off. And that's great in a world where you never want to touch that interface again. But in order to enable doing this with a robot, we had to demonstrate that we could safely cut all those wires and remove all those caps and then open up that valve, transfer fuel through it, and then safely close the valve and show that it was sealed so none of that fuel is leaking out. And that's what we were able to do successfully by using a series of real innovative tools. The key to our technology is that we design an innovative tool that can bridge the gap between a non-robot friendly interface and the robot itself. And so the technology is in the mechanisms and the innovation in the tool that can do that, use that robot to do that manipulation.
Now, Jill, you know as well as I do that nothing in NASA comes without an elegant acronym, and the next in this series of robotic refueling mission demonstrations is called VIPER, for Visual Inspection Posable Invertebrate Robot. Tell us a little bit about VIPER.
So VIPER is our next robotic tool that that is just launched on ATV-5, and it is a really cool tool. It has 3 different camera systems on board. The goal is that we are trying to take, we want to be able to inspect the worksite prior to doing any of the manipulation that I just was speaking about. So the camera systems that are on VIPER, one is a camera on a borescope, where it can go about 30. It's on a 34-inch length, and the last 2.5 inches of it can be manipulated in 90 degrees in 4 opposing directions. So the robot operators on the ground can actually command the end of the camera, or the little snake, and look around in different directions. So that's one camera. That camera is actually the smallest camera that has flown in space by NASA. It's 1.2 millimeters, and it is about the size of a dime. If there's one picture that'll we provided that shows just how small it is in comparison to a dime, and it does have a LED array around it, and it can see about 1/2 of a millimeter, about 2 inches away. So it's not the high resolution or high definition cameras that are, we're used to seeing down on the ground, but it was developed for the medical industry, and so it can, it has good enough to see very close up for what we want to see. The other real nice camera system that's on there is what we call the motorized zoom lens, and it's a custom camera that we built that has a 8 to 24 millimeter optical zoom lens, and we built a custom mechanism so that it can, with using just, again, very small technology. We're flying 1/2-inch stepper motors. These are the smallest motors, to our knowledge, that have ever flown in space. And it can zoom in from 2 feet away. It can resolve, like, again, a 1/2 a millimeter, about thinner than a credit card. So between the use of those two camera systems, and the third camera is just like our standard RRM cameras, where the robot operator uses it to focus on the tip and see what they want, so they can get a nice orthogonal view when they're doing the manipulation. So that third camera is a heritage, just like we've flown on our other 4 tools, but the 2 new cameras are the one that's on the borescope and acts like a snake, and then the motorized zoom lens on the side in the picture that you can see on your screen right now.
Jill, will the demonstration be carried out ultimately by the crew, the ground controllers, or both? And what is the schedule now that the hardware is on orbit?
Well, of course, space station robotic scheduling is, tied into multiple logistics with visiting vehicles, and our hardware has to be transferred outside of the GEM through the GEM airlock. So, so the folks are working to schedule it. Hopefully, we've been told next spring, unless a window opens up earlier this fall. We're ready when they are, and we're just waiting for the logistics and all the stars to align, so that they can start the transfer operations. Because we have 3 pieces of hardware to transfer out, the new Viper tool plus 2 new task boards that we are flying, it looks like the plan will be to do a transfer operation in one segment and then come back after everything has been mounted on RRM and start the robotic operations at a later date. So we're hoping, again, for the fall time frame for the transfer, but it may not be till spring when we can start the whole series of operations.
That's fascinating, Jill, and we certainly will be there along with you and your team as Viper takes the next step in the robotic refueling mission. Jill McGuire, the project manager for the robotic refueling mission from the Goddard Space Flight Center in Greenbelt, Maryland, joining us today. Thanks a lot, Jill, and have a great day. Appreciate it.
Great. Thank you so much. Bye-bye.